Hello everyone. In this video we'll be solving this problem on to find out the maximum capacity of the section which is provided. So this section is simply supported beam which has 2-point load placed at a distance of 2000 mm. They have given the section what they have used, that is 410 UB 53.7, which is of grade 300. So we need to find the capacity of this section in terms of load when it is laterally restrained throughout its length. Before solving this problem, let us understand the procedure how to find out this maximum capacity. So the maximum capacity in terms of design bending moment can be found out using this equation. This is given as per AS 4100. So mx star should be less than or equal to 5 msx and m star should be less than or equal to 5 mbx. So what is this msx and mbx? So as per AS 4100 table 3.4, 5 is the capacity reduction factor. It is considered as a factor of safety. MSX is the nominal section capacity about the x-axis and MBX is nominal member capacity about the x-axis. So what are this section capacity and what is the member capacity? Why do I want to find out this two different capacities is, so when a beam is loaded, it might undergo local buckling. The local buckling can be either a web or a flange, or it can undergo the global buckling where the torsion will take place. So when the beam is loaded, the beam might undergo the torsion like this, or there is a movement, rotation along with the translation moment. So this is the translation moment and this is the rotational moment happening simultaneously. So this is attributed to global buckling. So when the local buckling, to find out what is the local buckling, when does the local buckling will happen is termed as the section capacity. When it is attributed to global buckling, we need to find out the member capacity. Next, the section capacity of the flexural member can be found out using MS. We have got MS 5 times MSX. So this MS can be found out using Fi times Zt. Fi is the yield stress which is obtained from table 2.1 of AS 4100, whereas Z is the effective section modulus. Now to find out this effective section modulus, this is depend on the slenderness ratio. So what is this slenderness ratio is? It will tell us whether the section is subjected to elastic or inelastic local buckling effect. That means in simple terms we can say that whether the section will undergo elastic local buckling or inelastic local buckling. Now since this I section is made up of different web and flanges, we term this one as plate elements. So flange is a plate element, web is another element. So if it both has different slenderness ratio, then how can we find out what is the actual section slenderness ratio? For that, AS 4100 clause 5.2.2 defines that the whole section slenderness ratio can be found out after finding out the slenderness ratio of each plate element, either it will be flange or web, and what is its slenderness limit in terms of yield moment we need to find out along with the for each element. And when we divide the actual whatever we are getting slenderness of that section divide by the yield limit, and whichever has the higher value, that is we can attribute it to the whole section slenderness ratio. So now this is the table 5.2 which is given in the AS 4100. So we have different components here based on the plate element types, which is almost flat and circular and longitudinal edges supported, and based on that we have different mates, or based on residual stresses, stress relieved, hot rolled, cold deformed, and different sections are available, but we are sticking to the hot rolled in this section. Now we have web in the I element, in the I section. So we have web and we have flange. So this web, if you see that it is supported at top and bottom, so it is longitudinal edges supported on the both sides. We have both two options for that. One is uniform compression. So if this is undergoing uniform compression, then we need to select this category. Since we have seen that, we already know that if a beam is loaded, so the top portions will undergo compression and bottom fibers will undergo tension. So the web category element will come under compression at void edge and tension at other. Hence, the plasticity limit is 8248 and yield limit is 115. So we can say this is lambda suffix ep and this is lambda suffix ey. This is for the web. What about the flange? For the flange, you can see that the flange is supported only at the bottom for if we consider top, and for the bottom it is supported at the top. At the other end it is not supported. So we can call this one as one edge is supported, and it will be uniformly, either it is a top, it is uniform compression, attributed to uniform compression. Since we are looking only for the hot roll section, the plasticity limit will be 9 and yield limit will be 60. We found out these limits of this section for the whole section for web as well as flange. Now, based on these limits, this section can be categorized into 3 parts. That is, the lambda s, using the formula, we need to get the lambda s. That is, a lambda e will be attributed equal to the lambda s. And if it is less than or equal to, the slenderness is less than or equal to lambda sp, sp is nothing but the plastic limit, then that type of section is known as compact section. Okay, so the yield will as well as the plastic has a different moment capacity. Next, if whatever slenderness ratio we calculated, if it is lying between the plastic limit and the yield limit, then that type of section is attributed to non-compact. And if the slenderness ratio is greater than or equal to lambda yield sy, then that is called as slender section. So based on this different section, we need to find out the effective section modulus using the formula given. So if it is a compact section, then we can take the effective section modulus as S or 1.5 Z. If it is a non-compact, we need to make use of this equation here to find out the effective section modulus. And if it is a slender, then the effective section modulus can be calculated using this formula. And once we found out this formula, we will substitute and get what is the MS. And from there, we can find out what is its MSX and the actual maximum loading capacity. Let us solve this problem. The first and foremost step which we need to do is draw the bending moment diagram. So I have already drawn this. So what is the maximum bending moment diagram? So maximum bending moment of this beam is given by P times A, that is load times the distance. So A is nothing but 2 meter and P is the maximum load. After that we need to find out maximum section modulus. To find out the maximum effective section modulus, we need to find out what is my lambda suffix e, that is nothing but b over t square root of fy over 250. We need to get the dimensions b, t, fy for web as well as flange. So let us find out these details. I am referring the data sheet. So this is the data sheet given. So I am looking for 410 UB, which has 53.7 kg per meter weight, and I am noting down all these values, whatever required values to calculate the slenderness. So I am directly writing it. So the web has a thickness of 7.6 mm. It has its yield stress is given by 320 MPa and its breadth is given by 381 mm. I am substituting these values here, then I will get lambda e value as 56.7, and as I discussed earlier, lambda ey is 115 from the table 5.2. Now what is the ratio of this lambda e over lambda ey? So when I do this, then I will get 0.49. Okay, so this value, this is the ratio which is 0.49 for web. Next we need to do the same for flange. The dimensions of this is, it has a thickness of 10.9 mm. It has Fy of same as it is 320 mm, 320 MPa. It has a width of, which is given by Bf minus Tw over 2, which is 85.2 mm. Then lambda is calculated as 8.85, and lambda e over lambda ey for this flange is calculated as 8.85 over 60, so which is 0.55. Now the ratio is higher for flange, so I need to consider the lambda e as 8.85 instead of 56.7. Hence now after we have got this, then the lambda s value will be 8.85. okay, and the corresponding lambda sy is from the table 5.2 16. Instead of ey we are writing it as a sy, and lambda sp will be 9. Since lambda s is less than lambda sp, this is compact section. Okay. Now we need to find out z. So z is nothing but we can take minimum of s and 1.5 times z. So which is nothing but 1060, which is also taken from data sheet. When we substitute this, then msx will be equals to fyze, which gives me 339.2 kilonewton meter. So this is the maximum moment capacity of this. Now, since our case is fully restrained, so for the fully restrained, we know that m star should be less than 5 msx. So that is nothing but 0.9 times 339.2, which gives me 305.2 kilonewton meter. And we already know that this is my m star. I need in terms of load, maximum load. So m star value is 305.2 kilonewton meter, can also be written as P times EA. We already know this is the maximum bending moment for the section given load. We don't know P, we know 2, that is interval, and 305.2 kilonewton meter. Then P which we will get is 152.6 kilonewton. So this is the maximum load the section can withstand. So with this, I am ending this video. In the next video, we'll see the other case, which is full restraint at supports and partial restraint at the loading points. Thank you.